So today I wanted to talk a little bit about a library I worked on. It was almost a year ago, sort of before I joined JUXT, called Relic. I don't know how many of you have seen this, so I'm not going to assume any prior knowledge or anything like that. I'm going to assume everyone's going in without knowing what this library is or what it's about, what functional relational programming is, or anything like that. And what I want to do is give like kind of a high level overview of the sort of problem space that Relic is, kind of targeting. And I would like to give you a little bit of a taster for the library itself and sort of, what it's doing and kind of, what it might be useful for. Yeah, and that's pretty much it. So in terms of this session, I'm going to go through some slides and there'll be a brief, I'm not even going to call it a demo. I'm just going to go through a Clark notebook that I'd written ahead of time. And then if it's okay, questions at the end, but feel free to ask questions in chat and I'll get to them at the end, if that's okay. All right, so Relic, functional relational programming for Clojure and ClojureScript. So there's this paper called Out of the Tar Pit. Hopefully some of you will have seen this paper before. I mean, it's been out a long time. I would say it's been fairly inspirational for a number of individuals in the Clojure community. I know that for sure, and Clojure itself is somewhat kind of inspired by some of the ideas in the paper. The paper really talks about complexity in software development as being the kind of #1 problem. So not that surprising really as a kind of statement that, it talks about complexity. It talks about kind of how at the time object-oriented programming, what kind of complexity did systems written in that style exhibit, identified mutable state as one of the major causes of complexity, but also control flow and a few other bits and pieces. But ultimately it has this kind of story about state being very bad and talks a little bit about OO programming, logic programming, and functional programming, and their different approaches to state and order. And at the end of the paper, they propose a kind of a solution to the problem of state and some of this complexity, which they call functional relational programming. And this is not something people do really very much, directly, as the paper describes. But Relic is really it's a kind of love letter to this paper. So it is a pretty transparent kind of, implementation of what they talk about at the end of the paper as functional relational programming. So yeah, to summarize, state is bad. That's the kind of problem. Okay, so the problem that Relic is trying to address is the problem of state and mutable state, but also there's some subtlety to that one as we talk about functional programming, but certainly mutable state. But then there are other forms of state which we'll get on to. So what do we mean by state? Well, everybody would, if you've got kind of a mutable field in an object, right, that you're kind of banging on, we'd all call that state. Right, the state of the field changes over time, and in this example here, they've got a kind of they've got a little cache, right? So they've got this do calculation, and there's a little cache that's used to speed up the computation, and so that's a little bit of state that's been added to the program, right? It serves a purpose, serves a goal in this case, sort of performance. But this state is interesting because it has this property of it being kind of accidental. That is, it's nothing to do with the problem, the calculation itself. I mean, this is a kind of fairly contrived example, of course, but you've got some kind of basic arithmetic here, slow function call somewhere in there. But ultimately, our programs are full of this accidental state, right? That's one of the observations in the paper. Okay, and this is something we want to try to avoid. So there's this little table here. It talks about various different kinds of information or state. And certainly there are some bits of state that we cannot avoid, right? The user's input into the system, it's information from the outside world. The information space of the domain is something that we can't avoid. That's what we would call essential input state. And then there are different classes of states, right? So there are bits of state that are derived from that input, and they can have an immutable nature or a mutable nature, but ultimately they are both accidental in the sense that ideally we would only need to concern ourselves with the essential state. And of course, with this caching example, there is completely accidental state, right, which has nothing to do with the informational domain. It's not information that you kind of use to inform calculations. It's rather kind of a orthogonal kind of performance related optimization, something like that. So the solution that the paper talks about in functional relational programming, the idea of this kind of paradigm is to program with what they call rel vars, or relational variables. Relational variables are much like sort of tables in SQL, right? These kind of flat tables of tuples, records, which have various named fields. And what you do is you compose together relational variables as you would in SQL, to build up your information system, right? So, you might start with a table of customers and a table of their orders, and then you might compose those together using the relational algebra, so joins and projections and filtering to derive new information. And you do that relationally. So there's this kind of idea of derivation where you have your input state, and you derive from that input state kind of new relations, right? So relations from relations. And you use a relational algebra to do that. The computational side, so where you're doing arithmetic, kind of calculation, that kind of thing, they propose using functional programming to do that. So for example, in SQL, if you imagine, your select statement, you've got some expressions that do some arithmetic. Like we'd say, well, you could use functions to define that kind of thing when you're operating on scalars, say. So if you're operating non-relationally, then you can use functional programming, pure functions in particular. So they build this picture, and then they say, well, this ultimately is a kind of pure system and not very useful unless we can interact with the outside world. And for that, they describe a system of observers and feeders. So observers being processes that await change or are notified about change in the state of various relations, whether they're derived or not. And then feeders, those are the kind of mutators, right? They're kind of producing new information. They're maybe modifying existing information, that kind of thing. And they also talk about this idea of infrastructure, and infrastructure is kind of what makes all this possible. If you were to just do this naively, like, it's going to be very, very inefficient, right? You'd be calculating from the base data every single time you needed to know anything. Every time you change the state of the system, you would need to recalculate every single derived relation to be able to infer the observers that need to be notified of change. And so they talk about infrastructure as the means to perform this work efficiently. And also it's a place where you can hint, right, certain performance optimizations, certain things you might want cached, that kind of thing. And the idea is that they separate that from the definition of your system. And there's this notion IVM, so that's incremental view maintenance. And in my head, that is what this infrastructure they talk about, is really, really targeting. Incremental view maintenance is the idea that you may have some derived kind of SQL style view, and what you want to be able to do is change the base data that supplies the view with this information, and you want to be able to efficiently flow through the system change such that the view reflects the answers, but does an amount of work which is proportional to the size of the change to the input, something like that. Okay, so Relic is in this space, so it's sort of targeting these kinds of ideas. I'm not the only person doing this, so hopefully a few of you will have seen these like kind of little kind of hot words here. So differential data flow and the work of Frank McSherry at Microsoft Research. This is kind of as I would call the cutting edge in the field at the moment. There's a lot of Rust, right? There's a lot of data log, and there's this company called Materialize, which is doing incremental view maintenance for SQL, kind of a Postgres type SQL syntax, and that lets you build very, very sophisticated streaming systems using declarative SQL. So you can write your views, your aggregates, your joins, and Materialize will compile down to a very efficient incremental program that computes those results over time as your inputs change. Now I'm overdoing my own thing, so I wanted a library for Clojure. This stuff, there's a wrapper called Clojure3df for the differential data flow library, but I really wanted a Clojure native solution. I wanted a pure solution, purely functional, and I wanted to be able to use just maps, and not have to say ahead of time about my views or my input data or anything like that. So I embarked on my own little exercise to deliver this functional relational programming idea. Okay, so that's a little bit of background and kind of a little taster of the space. So Relic itself, it looks like, if you were just to look at it and look at the API and perhaps the README, you will see a pretty like simple little query interface where you have this idea of a database, and a database is a kind of value, and then you write a little query using a data DSL, and there's a queue function, and it returns you sequences of maps, right? So ultimately that's not kind of that interesting, it's sort of what you might expect of any kind of in-memory database system. It does use its own little DSL. I mean, it's not data log, it's its own thing. It's SQL inspired, so it is a little different to the other DSLs that typically use for this kind of thing. But ultimately, it kind of looks like an in-memory database, right? That's kind of the best surface level description. What Relic does is it takes that query definition and turns it into a directed acyclic graph. So it forms what's called a data flow graph from the query definition. And the result set of the query is defined in terms of flow novelty through that system. So whether that's basically additions or deletes, it's what we call what is flowed between the different nodes in the graph. And so in this example here, we've got this diagram where, we can imagine that you insert into the system some new products, and each statement within the Relic query is a node in that directed acyclic graph. And so from is like, just threads through from the base table. A where operator is going to do a filter, just like in SQL, and you can use a Clojure function with Relic. And what each node is going to do is it's going to apply the its operator, whatever that is, if it's a join, a where, a select, and it's going to determine what's changed, right? So what downstream from this node, what should change. So in this example here, like anything that depends on that where node must only see eggs, right? So that's kind of what's going on there. Here's a kind of, it's not entirely accurate, but just to give you a bit more of a feeling of kind of what's going on. A where is not very interesting, but here we have a join. So you have two relations, customers and orders. And we're going to flow basically changes from those relations into indexes. So these are kind of hash maps from customer IDs, so all the rows with that customer ID, same for orders. And then the join node is going to leverage those hash maps to be able to do joins, right, in a reasonable time. Because every time you change just one row, you don't want to rematerialize the hash table for the entire other relation, which we might have to do if we were doing this naively. And things like aggregates, right? This is kind of, again, like why you might want to use a library for this, not try and hand roll it. So aggregates have to use specialized data structures to be able to incrementally maintain their result sets. So things like sum, they use a binary tree, binary reduced tree, which minimizes the amount of work that needs to be done to maintain the sum as different nodes are added and removed from the data set. Okay, so that's just like a little bit of a taster for what Relic is actually doing and what makes it different from like a data script, say. So here's the value proposition. Yeah. So I want to be able to compute, as the paper describes, with relational variables. And for the functional bit of functional relational programming, I just want to use Clojure. I don't want some other thing, some other set of semantics that I need to learn. I just want to be able to use pure Clojure functions. Okay, so we're going to compose this new idea of relational variable or query with Clojure functions. The other thing that I wanted Relic the other property I wanted it to have was to be able to work with the data you already have. So there's no type requirement. You do not need to determine some schema ahead of time. It can work with any arbitrary object. You don't even need to have Eden values or anything like that. As long as your records or tuples are maps, everything else will work. It works best if you have maps with keyword keys, right? But that's about it. And it doesn't care if your data is nested or not. It's irrelevant. We can work with it. Relic needs to be able to react to changes. Now, this is one of the harder bits for a system like this to do, but it needs to enable you to build a reactive system. So it needs to enable you to build those observers that the paper talks about. And this comes in useful if you want to use Relic somewhere like, deploy it in a mobile app or a single page application where you would typically use reframe. Relic can serve the same sort of purposes as the reframe signal graph in that it can invalidate for you various UI components as the data changes that backs them. So as the model changes, your reagent components can be notified. Okay, and you can have like an R atom that is touched when a result set changes or a result changes. I wanted to be able to enforce integrity. So this is something that typical solutions in the Clojure space don't really give you many options for. But in particular, I wasn't so interested in kind of schema, like, schema and Mali, like kind of spec type constraints. I was far more interested in being able to do things like foreign keys, be able to apply constraints to arbitrary relations. So to be able to do things like say, well, any one time a customer can only have 10 orders, right? Those kinds of constraints, which are very, very hard to specify as universal statements in typical systems. But incremental view maintenance affords you the ability to do this. So that was something I wanted to capitalize on. And it's talked about in the paper as well. Integrity was a big part of the vision for functional relational programming. I wanted Relic to be lightweight and dynamic. So, I wanted to be able to use it. It's going to be in memory, right? I wanted to be able to use it as cheaply as I could in map. I just wanted to be able to chuck up a new Relic database whenever I liked, maybe locally within a function or for one particular batch job within a process. I didn't want to have to to bring in a big kind of heavyweight system and only have one Relic database for the entire system or anything like that. I also wanted Relic to be dynamic in the sense that the API is very late bound. Like you don't need to define anything ahead of time. You can issue new queries at any time. You don't need to define them They can be built at runtime. You can materialize and dematerialize queries whenever you like. So the Relic's API provides something that you would expect from a Clojure data structure. It's not like it's not like you have to sit down and write down all your relations and kind of all of your constraints and before you can do anything. It gives you a data structure and functions on that data structure, as you might expect for a regular Clojure map, say. Of course, yeah, as I sort of mentioned this, but to be cross-platform and usable in the browser was something I wanted to do. I was interested in being able to use the system for client work, so work with reagent applications and maybe React Native applications. So I found that something I wanted to do, and so Relic, I think, does deliver all of these features. So that's good. Okay, so enough slides. I'm gonna move over to a notebook where we're going to look at some queries and kind of talk a little bit more about how Relic is used, what it looks like. Okay, so hopefully you can see a little notebook now. So yeah. Okay, so what I'm going to do here is I'm going to def a little DB here, and it's going to be defed as an atom. And this is the first thing about Relic, right? It's, I think, in the README, Relic databases are just maps, right? So just a map. You don't need to like call a function to create a Relic database or anything like that. I'm going to put it in an atom because I want this to be a little bit terser than it would be if I had to thread everything around. But it's not necessary. Basically, Relic is a purely functional library. It has no state, like external state, mutable state, has no opinions about how you want to kind of manage state. And I'm going to find some little convenience functions again to make the Clark notebook a bit smoother. So T is transact. You see I'm just swapping on the atom and calling a transaction function. Q is query of my atom. Again, you see the Relic call here. I'm going to print the table for Clark. What if I'm going to speculate on the results of transactions? So I'm going to run a query as if these transactions have been applied. So that's going to be useful again. And then YOLO is, this is going to crash. That's I don't want to blow up my notebook. Okay, so with that said, I just want to get that out of the way. All right, so transactions. So transactions are data in Relic primarily. So you've got various different forms. So the first one here is basically how you typically seed a database. On the left of the map, you have table name. So in Relic, you do have the idea of tables or variables with names that you kind of bucket in your data into. This is fairly natural, of course, like most systems end up with something like this, but it's not like STDB. There's no universal space for documents. So I'm going to have some products here. I've got some bread, some eggs, and some cheese, right? And I'm just going to insert a collection of maps using this form here. So this is what we call a terse insert form in the docs. They're very useful to see the database. And the database itself then, if it's printed, just looks like a map with a table key name and a set of maps, right? And that's what Relic looks like. If you print it, that's what you see. You only ever see the data you put in and its essential state as regular old data. So it's sort of transparent. There's no like opaque object here that you can't look at. So query, you can just query data in a table, not very interesting. I mean, you can just get it out by name. It's just the same as calling get on the map, exactly the same. I'm going to use what if here to show a few more different forms. So we've got updates, right? This update here is you can apply a function to each row or to some subset of rows. And the function here, I'm going to use this little shorthand form where basically I'm going to apply an update of 1 to the price, add 1 to the price of each product. And you can see that the price changes to reflect that update. So you've got delete. You can delete one row, many rows using delete statement. So it's pretty much like SQL. Again, here I'm going to just delete cheese. You can see cheese is gone. We can compose transactions. The way in which they compose is you can use lists of transaction operations, or you can transaction function rel transact is variadic, so you can supply multiple transactions in sequence, and they will all be applied atomically, of course, as you might expect, and you get a new database value back. But here I'm going to do an update and a delete. So transactions is much more like you've got various flavors of upsert. So it's like insert or replace, insert or merge, or like insert or update, like various flavors of upsert that you might want. You could also write transaction functions. So if you apply a function of the database as a transaction, it would be a function of a database to a transaction, much like you might do in Datomic or in XCDB. So you can do dependent writes as well that way. And then the query form, I mean, you saw this in the slides. You basically got this vector. Each operator, call them relational operators, is an individual, is a kind of element of that top level query vector. And to do more, you just append to the vector. So say I want to like I've got from products where products skew eggs and I want to do some computation, I could append like a select node or a project node, and that would give me a new query back, which has that additional operation applied. So you've got everything you might expect from pretty much like a traditional SQL style query language. So you do have, you've got your select, you've got where, you've got join, you've got left join, you've got an aggregate function. And there are a few things we don't have, which we'll talk about. There's no recursion. So there's no right join or full outer join, but it's the things that people typically use for basic kind of SQL is all present. And of course has this incremental nature. So every one of these operators has this incremental for unit maintenance property, like they all behave using that query graph that we talked about before. So we've got sort here, again, very interesting, but still, just to give you a little bit of a flavor. Okay, so let's add some orders to this model. So we've got some products, we're gonna add some orders. Now I'm gonna supply a couple of orders here, one for me and one for John. We have some eggs and cheese, and John's gonna have some bread and cheese. So I've used a very natural nested map form here. Like this might be just something I had lying around. I'm going to just put that in a relation. Right, again, I said like I don't care if the data is nested. So again, I've got my database and looks as you might expect. So what we can do to build our system up is we can start deriving information from what we have in our base tables. So we're going to have a new relation here called order items. And what I want to do with this is I want to flatten out those order items within the nested maps. Okay. So I've got the query here, so from orders, and we're going to use this operator called expand. It's sometimes called, I think it's called unwind. It's like a denesting operator. Basically hoists up the elements of a collection, and their fields become part of the subsequent relation. And then we're going to just select a subset of the columns. I'm going to chuck away some of the redundant columns from that relation. And then you see I've got item quantity, product, and order ID. So I've now got a view of my order items, which is amenable for joins and so on. And as I change, of course, the orders, right, this is going to be updated. Okay. So I might have aggregate. So aggregate looks like this. So we've got projected sales here. I'm going to take my products. I'm going to take my order items. I'm going to join those together using a left join. And then for each SKU, I'm going to sum the number of items. And that's going to be the number of sales of that product. And I'm going to also like sum up the prices to get a kind of revenue projection. Okay. And then we can see we've got like 4 orders of cheese, 3 of eggs, and 2 of bread, and some values. So as I say, like Relic is, at this point, we've just been issuing queries, and they are going to be computed up front every time. Like it's just working like a normal database would. But the superpower here is, as we say, it's this view maintenance property. So the way we opt into that is using the mat function, or materialize. And this is something you can do at any time. You apply the materialize function with a query or many queries, and the Relic will return you a new database where those result sets will be maintained incrementally. So it will form the graph, right, and amend its kind of internal structure such that as we change, say, the orders, the products in those base tables, like with updates, inserts, or whatever, the change will flow through that graph, invalidate the result set of each node, ultimately ending up to very efficient updates, right? So we're going to be doing these kind of partial updates, work proportional to the amount of change we've actually done. It doesn't matter if we've got some massive aggregate, like over 100,000 rows, it will, you can have some like sublinear kind of pretty efficient update for that structure. And then when we issue queries, because the result sets are materialized, it's just like a lookup in a map, right? I'm not running anything. So the queries are then basically free for that relation. So it's shifting the work onto right, and we're using that graph that we talked about in the slides to do that efficiently. So yeah, we're going to materialize projected sales. It's not very interesting in a cloud note, but of course it's kind of like, just okay, now it's materialized. But if you have a big system and time this, so you see, you obviously get different timings. So I'm going to add another order here, and then we rerun projected sales. So when we do this, when we add this order here, this order will flow through the graph. And when we query projected sales, that's basically going to be free because that result set's been pre-computed. So it's very, very fancy caching. It's the best way to think about it, something like that. Now we're going to make this more interesting again. We're going to add a stock system. So we're going to have some stock counts for each of our products. So we've got 10 cheese, 5 eggs, and 4 bread, yeah. And then we're going to, again, derive some information. So just, take the projected sales data. We're going to join stock. And what I want to do here is I want to figure out how much stock I've got left, right? So it's a subtraction operation over the aggregates that we had before. So it's showing the composition, right? I'm like taking these queries and just like as data structures and passing them around and forming new queries off of that basis. So, the projected sales is itself a rel var, right, that I defined ahead of time. Going to join my new stock table, and I'm just going to write some new computations. So then we got this remaining quantity. Okay. So you can imagine, like, as you build this up, right, you get more and more sophisticated set of derived information. Again, that property of incremental view maintenance applies throughout this graph. And Relic understands things like the structure of queries being shared. So if you have multiple queries that are all based on the same thing, like, you'll only be flowing the data through the shared thing once, right? So the graph model for data flow is very, very well optimized to have many derived relations. Okay. So reactive programming. So we talked about the ability to react to changes being very important to build real systems. So I want to be notified when I'm out of stock, right? So I'm going to ask if there are any rows where the quantity is 0. This little operator is something we'll touch on later, but this is a null safety helper, because many Clojure numeric functions will throw if they encounter nulls. And because we have left joins and absence, so we have a kind of SQL style relational model, you often have to deal with that problem. That's the kind of problem with using Clojure as your language, but there's a little helper to make that a little bit more convenient. So the way that changes can be tracked, so you can watch a query or relation. So this is like materialize. The watch function will just return you a new Relic database, and it won't look any different, right? But machinery will have been allocated behind the scenes to allow change tracking to occur. So with change tracking, you have to have materialized the query. So Relic will do that for you if it hasn't already been materialized. And it will also associate some metadata to say it's going to be watched as well. So I'm going to be interested in the results of this query changing over time. And then we can use a variation of transact called track transact. And this takes regular transactions, same as a normal transact function. But instead of just returning you a new Relic database, it returns you a new Relic database alongside the changes to each of the watched queries. So in this example here, I'm going to take the changes and I'm going to look up my out of stock query, which is what I watched. Okay. And you can see what it returns is a set of added and deleted rows for that query. So this is kind of low level tool, right? You would have to build around this track transact to then get reagent integration or whatever, but it's enough, right? Like, so we can use this to build things like, basically to notify a reagent atom whenever a result changes, for example. Of course, if there are no changes, you won't see anything. It depends on what you changed, and you can have any number of queries be watched. So the other thing that we talked about is constraints. So what that looks like, so you have constraint operators. So you have check, you have foreign key, you have unique. And what we do with those is we supply operations, we supply expressions. So with check, for example, we supply an expression which must always hold, right? Must always return true. So this could be like any kind of, predicate, but of course you could use like spec or mali or something to do like schema type constraints. But here I'm interested in my stock counts, right? I want to never run out of stock. And the idea is, if I transact my database in such a way as I put it to put it in an invalid state, then I want to receive an exception, right? I don't want to be able to do that. Okay, so that's what constraints are about. So we're going to materialize the constraint as the mechanism you use to make it kind of start applying. And on the new database, if you were to transact against it, you will receive an exception if you put it in an invalid state. So here I'm going to like insert an order, which is going to take me out of stock, and I'll get a check violation error. And in the X info, the X data for that, I'll have like information about which constraint was violated, that kind of thing. So here's an example of the schema enforcement, like kind of, you can use check, unique, foreign key. We've got cascading deletes, so you can specify a foreign key relationship, which is like a child parent, where if the parent is deleted, I want to remove the children. And Relic is able to do that on your behalf. So if I issue a delete to, like, so this example, like if I delete a product, right, I want all of the stock to be deleted for that product as well. So you can specify that kind of thing as you would in SQL. But yeah, you can put constraints on any relation, right? So you're not limited to just saying, just specifying constraints on base tables and foreign keys. You can have constraints on aggregates or whatever you want. Again, that kind of implies incremental view maintenance. It's kind of necessary to be able to do that efficiently. Otherwise, you'd have to rerun every universal constraint anytime anything changes in the system. So that's basically my demo. I just wanted to show, I've got this little game called Clojure, which shows the reagent integration. And so this little game here, it's a little idle game where you you start out clicking this paren button, and you build up some number of parens to complete projects. So we've got this progress here. I don't know if you played Cookie Clicker or something like a long time ago. It's basically the same kind of thing. And so this game here, it runs reagent invalidating all these R atoms. It's an example of this kind of approach being used to build, real software, where like all of the state is in a Relic database, and all of the view invalidation that is necessary, where you typically use reframe, right, is done through Relic's observer, the kind of track transact and observation tools. So you can look at the code for Clojure. It's linked in the README, so you can look at the code for that, and I'll put some links together for people afterwards. But yeah, so that's kind of, it just kind of runs, sits there. Let's go back to my talk. All right. So problems. So these are things I would like to work on, or I think are problems with this approach. So mechanical reasoning is probably my #1 issue. So for example, like we don't have recursion. I've chosen a DSL where you have very explicit intentional operators, and each individual statement within a query or operator, is a different data flow node, and there's no reordering or anything like that. So you can, in principle, think about how this stuff will run and what a change to the input data would imply for downstream queries. But ultimately, I think this is a kind of essential problem with this kind of approach. It's true of most reactive systems, right? That you have very, very small inputs have outweighed effects, right, on the system, and it's difficult to predict exactly what the effect of a change would be and what the cost of that change will be to the system. Or it becomes more difficult. You have a kind of like action at a distance. So I find that quite difficult to deal with. I don't know if there's any way around that, but it's just something that I've observed. So the left join and null pointer exception issue. So left joins, I think, are an essential operator. Materialize does them, everywhere, SQL does them. But they have this issue, and we use Clojure as our functional language, whereas in SQL, like, your math functions, every function can accept null and return null. That only happens for a subset of Clojure, right? And so you typically have a problem where you will delete a row, say, and then cause a null pointer because a left join suddenly returns null, where a column had a value before. And you might be doing some math, right? And so that necessitated a little bit of work with the DSL, but this is still, annoying, very annoying. Of course, when you get an exception, because you've got this very sophisticated implicit mechanism for computing these results, like the stack trace is going to be pretty horrible, and it's going to have nothing to do with where the stack trace itself is going to reflect the data flow mechanism, not your query, because the query is just a data structure that's been interpreted by the data flow mechanism. So that's not great. We don't have recursion. There are a few other operators, semi and anti-joins, that I would have liked to put in. I did have recursion working. I still don't know if it's a good idea, though. Like, again, for mechanical reasoning, as soon as the fixed point recursion is in, or any kind of recursive operator, it just makes that so much worse that I almost kind of, part of me wants to say, look, if you want to do recursion, we just don't use this model. We use a different model for doing it. Of course, it's an alpha library. There's going to be bugs. I found one bug when I was preparing for this talk with unique constraints where they don't always work. And so they're probably many more bugs. I would like to fix those. And then there's lots of room for performance improvements. So like Relic is not too bad. Like actually for queries, it will like compete with the traditional kind of Clojure in-memory databases quite handily, but it can always be faster. And there are various techniques that differential data flow uses that I would like to use to speed things up. Much more batching can be done. Yeah, so there's lots of room for performance work, which I would like to get to at some point. So yeah, so that's it. So I've got 2 minutes left, I think, or maybe a minute and a half for questions. If anyone has any, thanks for coming. Thanks for listening. Yeah, give me a shout as well if you have any questions, or you want to talk about Relic or any of the ideas. I'm more happy to talk with people one-to-one or over Slack. So that's it.
Thanks for the presentation. One question about it. So Relic is implemented to just operate on some Clojure data, right?
Yes.
So it's not that it can run on top of a database and also do derivations like that? Yeah.
No. I mean, like the first thing everyone asks was sort of, like how can I use this to do sort of bigger than memory kind of like disks and distributed? And I know I was never targeting that. I mean, that's something that, so Materialize are doing that, they're on that journey. So there's a company, materialize.com, like that's Frank Mascherry's company, and they do this at scale. No, Relic is just about in process. Like I was really thinking about mobile apps and stuff. That's mostly what I was thinking about. And then like maybe just information processing, like in a bounded context where like I've got some like little problem and maybe in a batch job where I use Relic for all of the state management and the derivation, and then I'll just chuck it away when I'm done. Right. So that's kind of how I was going to situate it in programs. But yeah, it doesn't interop with any database or anything like that directly. So,
but
yeah.
I see like two pieces. Like there is this derivation graph, I guess, that you use, and then there's also the relational language thing. So what would you say is the advantage of using a relational language better than just Clojure code in order to calculate derivations?
Well, so if you're going to do incremental view maintenance, then what you're doing is you have to use some kind of declarative query language which is then interpreted or turned into a machine, a computation on your behalf. So like, if I write regular Clojure code, right, all of the caching, the directed acyclic graph, that would have to be coded up, right, in order to do the partial updates flowing through the system, efficiently. So, I mean, I don't think the approaches are comparable. I mean, I think if you don't need incremental view maintenance, right, you can use Clojure.set, like has like relational stuff like joins and things in it, right? You can do that, right? But no, Relic is about IVM, like that's really what it offers people. Like, and I suppose if you don't have that problem, if you don't need to react to things, and then it's less valuable. I mean, you could use DataScript or any of the other databases, of course, like if you don't need IVM.
Okay, so it seems that it's introducing more machinery inside the functional expressions that you would just not introduce when you're programming in Clojure as well, right?
Yeah,
yeah.
I think so. Yeah, I mean, so Clojure's place in this is that I want to be able to use Clojure data, and Clojure is used for the expression language, right? When you're computing with scalars. Then you use Clojure. Now I had those little nested vectors like inline. That's just sugar, like lambda sugar for Relic. Like you can just use Clojure functions pretty much everywhere. There's no requirement to do anything different. But you do have things like null pointers and stuff. Like you have just doing that can itself be problematic. So you need some help sometimes. Relic does give you some affordances in that direction. Yeah, I mean, and the relational algebra, of course, like is pretty good for derivation in the sense that it's an open, like access path independent kind of thing where you can kind of join things together over time, more and more sophisticated ways to produce data from different angles. Like it's context free. There's no like kind of preferred context or access pattern. So yeah, it can be good for like extensibility and kind of having a system that grows rather than is modified or changed. Yeah, we're Clojure programmers, so hopefully we'll understand that kind of thing. So Matt's got his hand up, I can see.
Yeah, hi there. Good talk, Dan. I sort of wanted to know, and I guess it pertains to using this in the small, like if you had to roughly describe what the kind of overhead is, what extra stuff you have to sort of have around, maybe to define in terms of memory footprint for like versus just having the data. Very broad brushstrokes, obviously depends on the amount of views you're maintaining, etc. But if you had to put a sort of feel on it.
Yeah, so I mean, like it depends on the operators that you're using. But I mean, there's each operator you can imagine having its own memory where it's going to need to keep indexes of the data, right? So yeah, the memory overhead is significant. Like you're going to have very many copies of the pointers. Like it's not necessarily going to be copies of the data, but you can have overhead in terms of memory. Things like, so hashing is used quite a lot. So Relic is set based. And you have a hashing overhead. So to be able to do the incremental view maintenance, like it needs to be able to remember old values. It needs to be able to look up values based on rows. There's no primary key at the moment, so it needs to always use a row's value as the key. So that there is a lot of hashing overhead as well. And I did talk about the mechanical reasoning being a problem, but yeah, I mean it entirely depends on the queries that you've materialized, how many of them that you have, their complexity. The complexity of your data. Like, but yeah, I mean, there is going to be overhead with anything like this, but typically programs will keep indexes and things anyway. I mean, if you're using reframe, there'll be like caches and like it'll be old versions of data like temporarily around and things like that. Yeah.
Are you doing anything at the moment, Dan? I was interested in a similar sort of question. Like, does Relic do anything to attempt to optimize and reduce that footprint? Is there any like compression or anything like that you're doing at the moment, or is that
Not
sort of TBD?
Yeah. Well, I have plans. I would say it's a pretty naive execution model at the moment. I mean, it delivers like, so you get this sublinear kind of thing where like aggregates can be invalidated, and the overall performance is sort of like to the order of complexity that I want. But there's lots of low-hanging fruit in terms of like tuning this. I mean, yeah, one observation is like we have to keep hashes of rows to other bits of like bookkeeping data, typically quite small on the value side there, but the key there is you've got to hash it. Like, but if we had primary keys, like we would only need to hash the primary key, right? There's things like that. There's occurrence map. So currently, again, it's set base, and there are some places where we need to keep memory of old rows, which is like the last version of a row that we've seen through the data flow graph. And that doesn't necessarily need to be done. It just happens to the way in which I'm flowing information that becomes necessary. But there are other ways in which it can work, which would be more efficient. So yeah, there are many internal optimizations one might do. Yeah, I think for the kinds of use case I'm thinking about, where you've got single page applications and whatnot with this fairly small data set, like I should think that it would be pretty reasonable to still, in terms of the overhead. Yeah.
The other thing that I was interested in, again, in the context of that cookie your parens game, I was just wondering, is the DB value itself like serializable in the sense that would it be viable to put this into local storage and like just dump it out to local storage when you close a page or something like that, or have something that's watching it's putting it in your local storage and then just reload it from there?
Yeah, I mean, it's just a data structure. So so the database always just looks like your essential state, right? You never see any of the like derived stuff. And so you can just serialize it as Eden or Nippy or whatever, bring it back up, and that's everything will flow. So you don't need to keep any of the incidental stuff around or accidental stuff around. So yeah, but I mean, there's no incremental serialization stories. There's no like kind of I mean, one could do so with transact, I suppose. You could be watching the base tables and things, and they're kind of, you can in principle, like, it's a map of sets, so you can keep change. This is a kind of delta from the previous set to the next one. You can have a log or something, but Relic doesn't have any opinions about how that would be done. I mean, but yeah, I mean, if it's again a smaller database, like you can just dump it in local storage, bring it back up, rematerialize the same views, and you're in the same state. Yeah,
I'm interested to build some kind of little toy, browser-based toy.
Yeah, cool. Multi-threading. Yeah. Well, so it's a data. It's eager, right? There's no laziness. It's eager. So when you transact, every single materialized view is fully invalidated, right? It's part of the transaction. So you only have a single thread. Like, well, I mean, internally I could use multiple threads, but I don't, right? And the cost for small databases with very few materialized views, it's like a data structure update. It's not like going off to the database and doing a lot of work. So I don't think multi-threading internally is necessarily what I would like to do. But having said that, I mean, I've got no opinions on partitioning, right? You can have many Relic databases, in different contexts, thread local ones, So and I think with the observers, you can build an information model which allows you to distribute work around, map reduce kind of stuff, perhaps. But yeah, again, the way to think about Relic is more like a data structure than a database, I think, in this respect. If that makes sense. It's a pure data structure where you just make an update, get a new data structure back. So there's no computational model that one needs to have in terms of threads and so on. It's like doing a bit of math in your program. Cool.
I don't think we've got any more questions. I don't know. Unless that was a serious question, I don't know. James has asked, when's Relic coming to XT?
This talk is not necessarily like a plug, because I think I wanted to do the tar pit thing and actually do the incremental view maintenance and have something in Clojure that did that. That's basically, but whether or not this is a good idea at all, and I'm talking about materialize the whole thing, like whether this is, so I think the problem of mechanical reasoning and, the problem of predicting the cost of one's change, like it is very, very difficult to deal with. And I think that there's an idealistic computational model where one could build tools to make this easier, but ultimately you are trading like control of the machine and its resources being part of the problem definition for like just giving it some guy on GitHub to like kind of, deal with, right? And I think that I don't know what the answer is. So for XT, I kind of like that XT doesn't have incremental view maintenance because it's so much simpler to think about in terms of, and particularly to optimize and that kind of thing. But having said that, I think, in certain contexts where we are basically already doing this with reframe, right? And it's, those kinds of incremental system, like, I think it's okay. I mean, there's certain places where a bit of reactivity and so on, a bit of implicit computations can be is bounded enough to not cause too many headaches. So yeah, I don't know. I don't think it's going to ST personally, but
Yeah, it was, well, mostly a jest at least.
Yeah.
But I could see us sort of being able to write something on top of the XE transaction block, as in once XT has decided whether the transaction is good or not, whether it should commit, then we could then you could imagine an incremental view maintenance library on top of that change log, if you like.
Yeah. I mean, but it's stream processing stuff. Like, I mean, you can hook it in, right, to that in that way. Yeah, I think one of the reasons for IVM that has been touched on with XT is constraints and like having this kind of universal constraint, like a check assert type thing. And I think that when you go down that path, like you do end up in this space, right? And so I suppose if we want to do something very fancy with constraints, you might end up with something that looks like IVM, whether or not you actually surface it to people.
I'd have to get involved in the construction of that blog, wouldn't it, if it was constraints?
Yeah, it's funny. Yeah, it's still in the tar pit. The original paper, the original title of my talk was There and Back Again, because I've come round to like maybe we should just write the glue and the because I think it's sort of they call it accidental state, accidental complexity. Like, and it's only accidental if somebody else can actually deal with it, right? And it's possible to do that, but without, you can ignore it. It's like, I don't know if you can ignore it actually. So maybe we need the buffers, maybe we need the mutable state, we need the caches to be explicit and intentional, and like to see the code that maintains them, right? With all of the problems that entails, it's still somehow like it needs to be in balance. Like there are reasons to do that, right? And so yeah, I very much agree. Like I'm back in the tar pit, and I'm happy. It's okay.
You're in the tar pit, so we don't have to be.
Yeah.
Oh, cool. Well, yeah, thanks very much for that, Dan. That was, really fascinating, really interesting bit of work. So, yeah, and Dan is going to be getting hold of an exclusive bit of JUXT merch, as he's now hosted a Safari session. And anyone else who has hosted a Safari session is going to be getting an exclusive bit of JUXT merch. But I'll explain more about that next week in the company meeting. Cool. So yeah, thanks for coming along all. And as always, if there's anything interesting that you've been working with or been working on, then get in touch and feel free to run one of these sessions. I think next time we're going to have, if all goes well, we're going to have something that actually doesn't relate to Clojure or even programming. I think we're going to have Ollie talking about solar panels, which should be interesting. A bit of a different Safari session, but yeah. So I think that may not be in 2 weeks' time, because I think that's the half term, but it will be pushed back, by another week. So yeah, see you all in 3 weeks.
Cheers, Vex.
Cheers all.
Cheers.
Thanks, Dan. See you all. Bye.